Hello, welcome to this lecture on modeling, analysis and estimation of three-phase unbalanced power network. In the last lecture, we have talked about the calculation of the capacitance of a general N conductor transmission line, and then from that we have derived that this capacitance matrix can actually be looked as a kind of equivalent admittance matrix, where essentially the diagonal terms are nothing but the sum total of all admittances connected at node I, and all the off diagonal terms are nothing but the negative of the admittance connected between node I and j. This is essentially the usual interpretation of the Y bus matrix. This is actually the basically the usual way in which we do derive the Y bus matrix, and from that we can actually calculate the capacitance to ground for any node, which is nothing but the diagonal term minus the sum total of all the off diagonal terms. So, from that we have derived an equivalent circuit for an N conductor transmission line, where we have shown by these green colored capacitances. These are nothing but the capacitances of individual node A, B, C and up to N to ground, and also we have shown the capacitances between any two nodes, which are nothing but CAB, CBC, etc., etc., etc. Now, essentially we are looking into the case of a three-phase transmission line. So, now if we do take this case of a three-phase transmission line, so let us look at three-phase transmission line. So, when we are looking at a three-phase transmission line, here we are of course not here of course we are not at as yet considering the ground conductor. So, that means we have got only three conductors, that is A, B and C. So, then therefore, I can write down the usual expression that VA, VB, VC by following the same process as we have already done in the last couple of lectures, that would be is equal to PAA, PAB, PAC, PBA, PBC, sorry PBB, PBC and PCA. And we have already looked into the expressions of all these coefficients, how to calculate them. So, then therefore, we are not repeating them. So, QA, QB, QC. Please note that all these coefficients can be calculated in terms of the distances between the conductors as well as the distance of every individual conductor with respect to ground. So, therefore, from here, so then therefore, this matrix we can say that it is essentially V vector is equal to some P matrix into Q vector. So, then therefore, I can write Q is equal to P inverse V is equal to CV. So, which translates into the case that QA, QB, QC is equal to CAA. Now, please note that we have already seen that all these coefficients would be actually positive quantities. So, then therefore, there is a matrix property that if we do invert any matrix of which all the all the elements are positive. So, then therefore, It has got a property that the diagonal elements will be positive, but all the off diagonal elements will be negative. So then therefore it would be CAA and then minus CAB minus CAC, then minus CBA, then CBB minus CBC, and then minus CCA minus CCB CCC. So, and then of course that is VA, VB, VC. So here of course this C denotes the capacitances, and this C in the subscript they do denote the phase C. So, I mean this we must distinguish. So, from here we can simply say that my CAG is nothing but, so I can say that my CAG, so from here I can simply say that my CAG is nothing but CAA minus CAB minus CAC, CBG is equal to CBB minus CBA minus CBC, and CCG is equal to CCC minus CCB minus CCA. Here also we must note the fact that because of this fact that this matrix P is a symmetric matrix, so then obviously this matrix C will also be a symmetric matrix. Now, so then therefore from here we can simply so if I have got phase A and then let us say phase B and then let us say phase B, so phase A, phase B conductor, phase C conductor. So I have capacitance say CAC, I have a capacitance CBC, and then of course I have a capacitance CAB, and then indeed we have so this is phase C, so this is phase C, and these C's are nothing but the capacitances, so we must again note that. And then of course we have and then we have so this is CAG, CBG, CCG. So that would be our equivalent circuit. Now this derivation is actually for the case of when this transmission line is not transposed. Now suppose I have got a transmission line and which has got transposed in let us say 3 different sections, and then my sections are let us say S1, S2 and S3 as usual, and then so then therefore we can simply find out that QABC from that earlier usual, that QABC would be F1 C123 plus F2 C231 and F3 C312 into VABC, and we have already defined these quantities f1, f2, f3, c1, 2 and etc. So we are not defining it. And of course here by the same method, C231 would be R phi matrix, which we have already seen, C1 2 3 into R phi, and C312 would be R phi into C123 into R phi inverse. So then therefore that would be the composite CABC matrix. So therefore we can say that so therefore I can say that this would be the composite. So this is the composite CABC matrix. Right. So that would be the composite CABC matrix. So by this method, so by this expression, we can find out the composite, or rather the final capacitance matrix of any three-phase transmission line when it also undergoes the operation of transposition. Okay. Now let us look one numerical example that will actually. So we consider one three-phase line. Please note that we are only talking about three-phase line. So phase A, phase B, phase C, and the distance between them is 14 feet. This is also 14 feet, and the distance from ground. So this is ground, say ground. This distance is 40 feet. So if this is the configuration, then I would like to find out the capacitance matrix. So for this, I know that DAB is equal to DBC is equal to 14 feet. I also note that DAC is equal to 28 feet, and I also note that HA is equal to HB is equal to HC is equal to 80 feet, because HA is nothing but the distance between any conductor and its corresponding image conductor. So then therefore if phase A is at a height of 40 feet from ground, so then therefore its corresponding image conductor would be at the depth of 40 feet from the ground. So then therefore the distance between phase A conductor and its corresponding own image conductor would be 80 feet, and HAB would be essentially, so it is nothing but so HAB would be basically, now what is HAB? HAB is nothing but the distance between original phase B and the image conductor of phase A. So then therefore it would be this distance. So this distance is 80 and this distance is 14. So then by applying Pythagoras theorem, I can find out that it says 80 square plus 14 square feet. So that turns out to be 81.2 feet. It is roughly 3 feet, 81.3 feet. And then that also would be equal to HBC. So that also is equal to HBC, right? Because from between phase B, so then basically HBC is nothing but the distance between phase C conductor and the image conductor of phase B. So then therefore that also would be equal to HBC, and HCA would be nothing but by the same token 80 square plus 28 square, right? So that out to be is 84.8 feet, and the radius is given as r is equal to 0.0359 feet, right? So now, so from this, so then therefore, I mean, these quantities are given and all the other quantities we have calculated. So now we calculate PAA. So now PAA, and that now here you see, because here HA is equal to HB is equal to HC is equal to 80 feet. So then therefore PAA also would be equal to PBB, and also would be equal to PCC is equal to 1 by 2 pi epsilon log HA by R. Right. So that is the expression, because of this simple fact that HA, actually basically PA is equal to 1 by 2 pi epsilon log HA by RA, PB is equal to 1 by 2 epsilon into log HB by RB, and PCC is equal to 1 by 2 pi epsilon into log HC by RC. But because HA and HB and HC are equal and RA is equal to RB and RC, because all these conductors have been assumed to be of identical diameter or rather radius, so then therefore they will be all equal to each other. And epsilon is given by, I know that it is 1 by 36 pi into 10 to the power 9, right? So then therefore from here I can write down that PAA is equal to PBB is equal to PCC is equal to 18 into 10 to the power 9 into log 80 by 0.0359, right? And its dimension would be farad inverse per meter, right? Now it would be, so that I can say that 18,000 into log 80 by 0.359 mega farad inverse into meter, right? That I can say. Now I would like to convert it into miles, because the length of this conductor is given in miles. Now we know that 1 mile, now 1 mile is equal to, it is known that 16.1609.344 meter. So then therefore PAA is equal to PBB is equal to PCC is equal to, now I convert it into mile, so it will be 18,000 divided by 1609.344 into log 80 by 0.0359 mega farad inverse mile, right? So that is the case. So now if we calculate this, it comes out to be 11.185 log 80 by 0.0359 into mega farad inverse mile. So you see this quantity now 11.185, we can simply take it as it is henceforth, because This quantity is nothing but independent of the uh, line distances as well as their radiuses. So, this quantity is constant. So, then therefore, this turns out to be, if I now do this calculation, it turns out to be 86.28 mega, right. Similarly, PAB is equal to PBC, that would be, now I will take 11.185 as it is, because log HAB, or rather HAB by DAB. Now HAB is say 11.185, HAB we have computed 81.2, so log 81.2, and DAB is 14, so that turns out to be 19.66 mile. And PAC is would be, again we take this quantity constant 11.185 log HAC by DAC, and this is 11.185 log HAC we have already calculated 84.8, so it is 84.8 divided by, it will be 28, so that turns out to be 12.39 mile, right. So then therefore we have calculated everything. So what is my P matrix now? P matrix is PA, so it is say 86.28, then PAB is 19.66, and then PAC is 12.39, right. It is again 19.66 because it is symmetric, and it is 86.28, and PBC is 19.66, and now PCA is 12.39, and then it is PBC is 19.66, and PCA is 86.28. So this is the P matrix and its unit is mile. So now if I do its inverse, so therefore C matrix is equal to P inverse. If I do the inverse by using some computer code, it turns out to be 12.34 minus 2.504 minus 1.19 minus 2.54, 12.75 minus 2.54 minus 1.19 minus 12.34. This is nanofarad per. So this becomes nanofarad per mile. So from there we can calculate CAG is equal to this minus this. So that's how 8.606 nanofarad per mile CBG is equal to 7.667 nanofarad per mile, and CG is equal to 8.606 nanofarad. Right. So that's how we calculate the capacitance matrices of any three-phase transmission line from its distances. So here what we have done, so we have shown that given the geometrical configuration of any transmission line, I mean when we are talking about the geometrical configuration means that what is the distance between the conductor and what is the distance between of all the conductors from ground and etc etc. So essentially we have shown an example that where if I have the geometrical configuration of the transmission line, and if I have also the information about their information about their radiuses, so then from that, by following a very simple step by step method, we can find out the capacitance matrix. Now here we have taken a very simple case where all these conductors are at the same level, but suppose for example I have a case that where say suppose for example I have a case, say phase A is here and say phase B is here and say phase C is here, and I have my ground. So let us say that phase A is of some distance, say 40, let us say this distance is say 35, say for example, and say this distance is 45 for example, and I have got, say for example, this distance I know say 15, and this distance I know say 15. Suppose I know that this distance is 15. So from these geometrical dimensions, I can always calculate what is the distance of this. I can always calculate by applying Pythagoras theorem and all that, and by applying simple geometry. I can also calculate that what is the distance. So I can always calculate this distance by applying simple geometrical concepts. I can also calculate by applying simple geometrical concepts. I can also calculate the distance by applying simple geometrical concepts. So this is A, this is B, this is C. So this is essentially the distance I can calculate, and once I calculate these distances, after that we can simply apply this formula, so without any problem. So then therefore, as we can see that by employing these formula and just by knowing the geometrical configuration of any transmission line, you will be able to calculate the capacitance matrix. And here, as also we can observe that similar to the case of the series impedance matrix, this capacitance of a three-phase line is also essentially a 3 cross 3 matrix. So then therefore, for any transmission line, both the series impedance matrix and also the shunt charging capacitance matrix are both 3 cross 3 transmission line. So we basically finish this lecture here, and in the next lecture we will look into the final aspects of the calculation of the capacitance of a three-phase transmission. Thank you.